Okay, so with that, I'm very happy to welcome Robert Brandenberger for today's talk. Robert Brandenberger did an undergraduate degree in physics at the ETH in Zurich before moving to the United States and doing a PhD at the University of Harvard. He did a postdoc with Hawking at Cambridge in the Department of Applied Mathematics and Theoretical Physics there, as well as at UC Santa Barbara. He held a faculty position at Brown University before moving to McGill, where he is now a Canada Research Chair Tier 1. He's also an affiliate member of the Perimeter Institute, is a fellow of the American Physical Society and received many honors. I'll just mention two. He received the Sloan and Killian Research Fellowships, very prestigious research fellowships. He works in cosmology, and among other things, he developed string gas cosmology with Qumran Wafa. Today, he will be talking about is inflationary cosmology consistent with fundamental physics? Please, Robert.
So thanks a lot for the invitation to speak. It's a great pleasure to address a very diverse audience. So if you see a title like this with a question mark, then you won't be surprised to hear that I will try to convince you that the answer is no. Okay, but I should also tell you, to be honest, that most of the people in my field, most of the high-energy physicists would disagree with my conclusion. So just to lay the cards out. So now my talk will be divided into two parts. The first part is going to be absolutely non-controversial, but there are going to be some surprises for many of you. And then the second part of the talk is going to be very controversial. And so what I will do is I will stop after the non-controversial part and ask for some questions of clarification already then. Okay, so good. So the uncontroversial part of the talk is going to be the lengthy introduction. And in the introduction, I will convince you that there are more ways to explain what we observe today in terms of the large-scale structure of the universe. There are more ways than just inflation. And then I'll give a brief review of the inflationary scenario. So this is going to be the uncontroversial part of the talk. And then I will go and talk about attacks on inflation and two sets of attacks, one coming from string theory, and this goes under the name of the Swampland criteria. Hopefully you see my cursor. And then the other set of attacks, which are more general, they come from more pure quantum gravity considerations. They are analogous to Penrose's cosmic censorship conjecture. So, and then I will wrap up. So this is the menu for today. So in cosmology, we want to explain what we observe. And one of the things that we observe today is the microwave background. So this is a projection of the sky onto a plane, like the projection of the surface of the Earth onto a plane. So you see the celestial equatorial plane, the celestial North Pole, the celestial South Pole. And the color indicates the intensity of the microwave background radiation, which is reaching us from all directions in the sky. Now, in any direction of the sky, the microwave background is observed to be a black body, and so we can convert intensity to temperature. And here you see this beautiful temperature map. So you see black, 0 temperature, bright red, 3.6 degree temperature, and you see that the temperature is incredibly isotropic. So if you zoom in and you look with much more powerful telescopes, then you start to see small amplitude anisotropies popping up. So here's a patch of the sky where the temperature is slightly higher. Here's a patch of the sky where the temperature is slightly lower. And the temperature differences are about 10 to the minus 5 of the average temperature. Okay, so now the way that we physicists describe the data as we try to quantify them. We don't just look at patterns like this S here for Stephen, but what we do is we expand this map in spherical harmonics, and we plot the amplitude as a function of the spherical harmonic or angular size. So, okay, so this is the same data of the previous map, which is put through this black box spherical harmonic filter. And the data points are the black dots with statistical error bars for small angular scales and with some systematic uncertainty in large angular scales. And the red is a 6-parameter curve which fits the data reasonably well. And so the question I'm sure you'll be asking is, who designed this 6-parameter curve? And in fact, this is where some of the surprise will come. So now, none of this data, the isotropy of the microwave background and the small amplitude anisotropies, none of those can be explained in terms of standard Big Bang cosmology. And one of the reasons is expressed in terms of this horizon problem. So this refers to the isotropy of the microwave background. So in this slide, the vertical axis is time, the horizontal axis is space, and this point, which I'm indicating with my cursor, is the Big Bang. This point in time, which I'm indicating now with the cursor, this is when the microwave background was released, so it's time of recombination. And if we look at microwave photons which come to us from opposite directions in the sky, then we see these photons emerging from regions which in standard Big Bang cosmology never could have been in causal contact because the past light cones of A and B did not intersect. So this is the horizon problem. Standard Big Bang cosmology cannot explain the isotropy of the microwave background. And standard Big Bang cosmology cannot explain the origin of anisotropies either. And this is explained in terms of this sketch. So here, the vertical axis is again time. The horizontal axis is space, co-moving coordinates, so coordinates which expand as space expands. And here, this horizontal line is drawn at the time of equimatter and radiation. And this time plays an important role because it is only after this time that anisotropies can start to grow in amplitude. So this diagonal line is the standard Big Bang horizon. And according to causality, there can be no causal influences on length scales larger than the horizon. So now we observe today inhomogeneities on very large scales, on scales which were larger than the horizon, than the standard Big Bang horizon at the time of equimatter and radiation. So we see fluctuations today. The seeds for fluctuations already had to be present at the time of equimatter and radiation, and this is acausal from this point of view of standard Big Bang cosmology. So standard Big Bang cosmology can neither explain the isotropy of the microwave background nor the small amplitude anisotropies. And therefore, the idea is that we have to go back to the very early universe, modify the very early universe in order to explain the data. So let's set up the framework that we use. So I won't have that many equations, but here are two important equations. So this is the metric of space-time that gives us the separation between events. T is time. These x's are these coordinates which expand as space expands. And A of t is the scale factor, which indicates the spatial radius of a chunk of the universe. And h is the expansion rate. It depends on time, the A dot over A. So this is just a set notation. Good. So the question I want to come back to now is, who first drew this red curve? And the people who first drew this red curve are Peebles and you in 1970. and Zeldovich and Zunyaev, also in 1970, 69, 70. This is 10 years before inflation. So to convince you of this, here is a plot from the Zeldovich-Zunyaev paper. So it's a poor quality reproduction. So this is time. The horizontal axis is co-moving coordinates. This diagonal line is the standard Big Bang horizon until the time of recombination. And actually, what is plotted here is the Jeans length, which is the length above which fluctuations are frozen in and below which fluctuations oscillate. And this is, in standard Big Bang cosmology, before the time of recombination, it is equal to the horizon. So what Zeldovich and Zunyaev, and in parallel Peebles and New discussed, is the following. They said, let's assume that we have some primordial inhomogeneities. They will then start to oscillate once the wavelength becomes smaller, becomes equal to the horizon, standard Big Bang horizon, and different wavelengths will perform a different number of oscillations between when they start to oscillate and the time of recombination. So this wavelength, the wavelength which enters the horizon right at recombination, will have done 0 oscillations. And so we will catch this wave at maximal amplitude because they are standing waves. And maximal amplitude inhomogeneity will lead to maximal amplitude anisotropy. Then there's a wave that has done 1/4 of an oscillation. We catch it at maximal velocity, minimal amplitude, and so on. And so based on this picture, it was predicted 10 years before inflation that we will get acoustic oscillations in the CMB angular power spectrum. And such an initial spectrum of density perturbations was already known in 1970 to give a good description of the distribution of galaxies. So the answer is that it is Peebles and Yu and Zunyaev and Zeldovich who first discussed this curve. It has nothing to do with inflation. Now, this diagram from the Zeldovich-Zunyaev paper had a second part, a lower part. And here it's the vertical axis is the amplitude of the density perturbations. The horizontal axis is wave number. And these oscillations manifest themselves also in the oscillations in the matter power spectrum. And this is called baryon acoustic oscillations. So acoustic oscillations in the CMB angular power spectrum, baryon acoustic oscillations in the matter power spectrum were predicted 10 years before inflation. The physics was very well understood, and it has nothing to do with inflation. And this is a part of the absolutely non-controversial part of our talk. Now, the question which was not addressed in 1969, 1970 is how does one obtain such a spectrum of primordial fluctuations on scales larger than the standard Big Bang horizon? And it is true that inflationary cosmology is the first scenario based on causal physics, which yields such a spectrum, but it is not the only one. And so now I want to elaborate on what are the necessary conditions for an early universe theory in order that it give such a spectrum. Okay, so first of all, I have to tell you about the difference between horizon and Hubble radius. So the horizon is the forward light cone of a point on the initial Cauchy surface. So the horizon is the region of causal contact. Whereas a Hubble radius is a local concept. It is at any given time, the Hubble radius at that time is the inverse expansion rate. Now the Hubble radius plays an important role because it is relevant for the dynamics of inhomogeneities. Inhomogeneities with wavelength smaller than the Hubble radius and Hubble radius oscillate. Those with a wavelength larger than the Hubble radius are frozen in. Now, in standard Big Bang cosmology, the Hubble radius and the horizon are the same. And therefore, there's a horizon problem. So in any theory which can provide a mechanism for solving the problems of standard Big Bang cosmology, the Hubble radius has to be very different, very much smaller than the horizon. So this is the first criterion for a successful early universe scenario. The horizon has to be much larger than the Hubble radius. Otherwise, we can't explain the isotropy of the microwave background. Then, if we want to have a causal mechanism for generating structures locally in time, then the length scales for fluctuations which we observe today have to start out smaller than the Hubble radius at early times, because we want to be able to move matter around on that scale over one Hubble time interval. So this is the second criterion. Now, if we want to start fluctuations as vacuum fluctuations, then fluctuations have to evolve for a long time on super Hubble scales in order to be able to produce something that looks classical. But if you start with classical fluctuations, there's no need for this third criterion. And finally, you need the mechanism which satisfies the first three criteria also has to produce a roughly scale invariant spectrum of fluctuations. And scale invariant means that if you pick a sphere in space, then the relative fluctuations don't depend on the radius of that sphere. So that's what scale invariant means. So these are the four criteria for a successful early universe scenario. And inflation indeed satisfies all these four criteria. So this is the first time I mention inflation. So inflation is a modified theory of the very early universe where you assume that there's a period, an early period between starting at T sub I and ending at time T sub R, where space expands almost exponentially. So this is the space-time diagram of inflation, vertical axis time, horizontal axis physical length scale. So in inflationary cosmology, there's a pre-inflationary phase and there's an initial singularity. So this is a space-time diagram of inflation. So during the period of inflation, if you have exponential expansion, the Hubble expansion rate is constant. So the Hubble radius is constant. But space expands exponentially, therefore the horizon expands exponentially. So inflation produces this exponentially increasing divergence between horizon and Hubble radius. So first criterion satisfied. Then if we look at this red curve, and this red curve is a physical wavelength of stuff that we observe in the universe, for example, the quadrupole of the microwave background. So this is a wavelength fixed in co-moving scales. And during the period of inflation, the physical wavelength expands exponentially. So as long as inflation lasts sufficiently long, length scales of stuff that we measure today start out sub-Hubble at the beginning of inflation. So therefore, in the region where we can causally produce them. So criterion 2 satisfied. Fluctuations evolve for a long time on super Hubble scales, criterion 3 satisfied. And the reason why you get an approximately scale invariant spectrum is that this phase is approximately time invariant. So this is one mechanism. Another way of satisfying all criteria is to take a bouncing universe. So here is what I'm assuming about the size of a chunk of the universe, so the A of t as a function of time. I'm assuming you start in a contracting phase. Then there's some new physics that gives you transition to expansion. And this is standard Big Bang-like expansion. And this is, for example, the time reverse. So this is a bouncing cosmology. And here on the top, you see the space-time sketch. So this is a bounce point. Again, the vertical line is always time, horizontal line is here, co-moving coordinates. So in the expanded phase, this is a Hubble radius. In the contracting phase, this is a Hubble radius. And so where's the horizon? Well, time runs from minus infinity to plus infinity. Horizon is infinite. Criterion 1 satisfied. Here, I've shown you the different co-moving scales. They start out sub-Hubble. So criterion 2 satisfied. Scales propagate for a long time on super-Hubble scales. Criterion 3 satisfied. And it turns out, and you have to accept this, that if you start with vacuum perturbations in this symmetric bouncing scenario, you get a spectrum of scale invariant perturbations after the bounce. So this is another paradigm with which you can realize all of the ingredients for successful late-time cosmology. Okay. Now, another way to satisfy all of these criteria is to have an emergent universe. So here I postulate that there's an early phase, maybe a phase in which space-time doesn't even exist, or a space-time which I model here as a quasi-static phase, so size of space constant. And then there's a phase transition to the standard Big Bang phase of expansion. So again, no inflation here. This is a time of the phase transition. So this is my postulate. This is the resulting space-time diagram, time, space. This is the phase transition. This is the standard Big Bang phase of expansion. This is this quasi-static early phase. And again, maybe this quasi-static early phase is infinite in time. The horizon is infinite. So the horizon is infinitely larger than the Hubble radius. This is a static phase, so the wavelength of fluctuations doesn't change in this phase. So it is, to give you numbers, it is typically a millimeter, which is many, many orders of magnitude in the Planck scale. So again, criteria 1 through 3 are trivially satisfied. Hubble radius much smaller than horizon. Scales start out smaller than the Hubble radius, and scales evolve on super-Hubble scales. Now I will ask you to accept the fact that if you start with classical thermal fluctuations in this early phase with a particular scaling called holographic scaling, that then you also get scale invariant perturbations. Okay, so the bottom, so what I've presented you now is 3 early universe scenarios with which we can explain all of the data. And there's no, I didn't cheat here. I think everyone would have to agree with this conclusion. So now, I'm going to later on attack inflation. So I will first introduce you to inflation. So inflation has become the standard paradigm of early universe cosmology. And the idea is that there is a phase of almost exponential expansion in the early universe. So it solves some problems of standard Big Bang cosmology. And it provides a causal mechanism for structure formation. So I agree with that. It has an initial singularity. So how do we get inflation? So if we describe space-time using the Einstein equations, then we need some strange form of matter to give us this exponentially expanding universe. We need a strange form of matter which has pressure almost equal to minus the energy density. And if we want to get that, then we need to introduce slowly rolling scalar fields. So, okay, no one has ever seen a particle in the lab which corresponds to a slowly rolling scalar field. People have now measured, I've seen a particle which corresponds to a scalar field, maybe not a fundamental scalar field, but a scalar field, named the Higgs field, but it does not give you, using the Einstein-Hilbert action, it does not give you inflation. Anyway, So this is how you get inflation. You have to introduce this slowly rolling scalar field. And then quantum vacuum fluctuations during the phase of inflation, they evolve to provide you the right kind of fluctuations. So now let's go back to this slowly rolling scalar field. So if we have a scalar field, and if we treat it as homogeneous in space, then this is its equation of motion. So this is like F equals ma. This is the force that comes from the potential of this scalar field. And a priori, you have no recipes for choosing this potential. And then, so this is the acceleration, this is the force, and in an expanded universe, there's a friction force. So this is the general equation of motion for a scalar field. Now, in order to get inflation, the scalar field has to roll very slowly because you want the potential energy to dominate over the energy of motion. Otherwise, you don't get inflation. So therefore, the slope of the potential has to be very small in natural units. So V prime is a derivative of V with respect to the field. And V prime over V times n Planck has to be much, much smaller than 1 in order to get inflation. And this is a condition that doesn't only have to occur at one point in time, but has to occur over a long period of time. And this leads to the second condition. Okay, so to get inflation, you need to postulate a scalar field. This scalar field has to obey this condition on the first derivative and this condition on the second derivative. And if you don't want to fine-tune your initial conditions for the scalar field, then the range of scalar field values has to be much bigger than n Planck. So this is required if you want inflation to be a local attractor in initial condition space. Okay. Good. So now I will make the transition to the provocative part of my talk. But this still is not provocative. So I should ask the question, does inflation actually emerge from a ultraviolet complete theory? It is self-consistent as an effective field theory. So let me now stop for questions before I enter the controversial part of my talk. So I guess you're all waiting for the controversial part of my talk.
Maybe so. I don't see any questions at this point.
Which I like.
So okay, I guess you should just continue. Thank you.
So the first set of objections towards inflation come from or motivated by superstring theory. They go under the name Swampland conjectures. And the second set is more general. They go under the name Trans-Planckian censorship conjecture. Okay, so Swampland criterion. So I am not a string theorist. So, but I'm willing to defend this statement here. So if you just stick to effective field theory, then there's a huge landscape of possibilities. You can work in any space-time dimension. You can have any number of scalar fields. You can have any shape of the potential, any field range. There are no rules, no constraints. You can get anything you want. In fact, there's a theorem that says, you give me the scale factor you want, I can give you the scalar field potential, which gives you this cosmological evolution. So absolutely no rules. So compared to this, superstring theory is very constraining. It says that there's only one dimension of space-time which works. It happens to be 10. So maybe, but that's not a problem. I can talk about that a little bit later. Scalar fields all have a geometrical origin, and their potentials are all determined or all constrained. So the bottom line is only a small subset of all effective field theories is consistent with string theory, and the rest live in the swampland. And this is an illustration. It's not my illustration. So in green, you have this swampland of effective field theories. And then if you accept string theory, then there are only small islands, habitable islands, which stick out from the swamp. And what are the criteria for these islands? And I'll focus on criteria on scalar fields. So first of all, such an effective scalar field theory, which is consistent with string theory, is only valid for a field range smaller than order 1 times n Planck. But for slow roll inflation, I just argued before that we need field ranges bigger than n Planck. Now, potentials which emerge from string theory, they are typically steep, and their second derivative is tachyonic if you happen to be at a local extremum of the potential. So these are these swampland conjectures. There are 3 constants that appear here, D, C1, and C2, and they're all postulated to be of the order 1. So these are these conjectures. And so now will come a slide which I cannot defend very well because I'm not a string theorist. But so where do these conditions come from? So any scalar field is a modulus field in string theory. It has some geometrical origin in string theory. And if you move this field for more than n Planck, then you deform this internal space such that a huge number of new states become low mass and must be included in the low energy effective action. In terms of a simple example, I can actually demonstrate this. So this is the origin of this distance conjecture. Now, the constraints on the shape of the potential and the steepness of the potential come from the fact that in string theory, these scalar fields are stabilized by stringy effects. And typically you get quadratic potentials. And a quadratic potential is steep. And details of that you can read in this paper. So this is a very low level understanding of where these swampland criteria come from. So these are the conditions: small field range, steep potential, very tachyonic. These are the conditions for inflation: large field range, shallow potential, very small second derivative. So you see, slow roll inflation is in the swampland. False vacuum inflation is in the swampland. However, there are ways to get inflation that do escape from the swamp, at least at this level. For example, warm inflation. So if you have your scalar field coupled to many other fields such that the other fields determine the friction, so then you can escape from the swamp. So this is the first set of objections. Now, the second set of objections come from, are called the Trans-Planckian censorship conjecture. And these are based on work that I did almost 20 years ago with Jerome Martin. We had this space-time diagram of inflation, which you saw before. So time is the vertical axis, space is the horizontal axis, physical spatial dimension. This is a period of inflation from Ti to Tr. And as I showed you before, inflation is successful because wavelengths which we observe today are brought back to be smaller than the Hubble radius. This is the Hubble radius at the beginning of inflation. But if inflation is only a little bit longer, lasts only a little bit longer than it has to explain the homogeneity of the microwave background, then you find that scales that we observe today have a wavelength smaller than a Planck length at the beginning of inflation. So back in 2002, we said that, well, we definitely need quantum gravity in order to really be able to explain what fluctuations do. All these fluctuations which we observe today in inflationary cosmology come from this Trans-Planckian region of ignorance. But now the new twist to this, which was proposed by Bedroya and Waffa, after I gave a talk on this Trans-Planckian problem at a string theory workshop a year and a bit ago. They said, this sounds a bit like a new postulate. They said, maybe there's a postulate that says that no Trans-Planckian modes ever exit the Hubble horizon. So again, this is the equation which we've seen before, the line element of space-time. This is the Hubble expansion rate. The Hubble radius is the inverse of that. And the Trans-Planckian censorship conjecture mathematically means the following. You start at some initial time t sub I. You start with the Planck length, and you let this physical length scale expand until a later time t sub r. At this later time t sub r, this is the resulting physical length, and we demand that it be smaller than the Hubble radius at this later time. So what I'm circling now with my cursor, this is a mathematical form of this Trans-Planckian censorship conjecture. Okay, so now what you can't find in Bedroyer-Waffa's paper, what was actually, and you can't find it either in the follow-up paper that I wrote with Marilena Loverde and Bedroyer and Waffa, is some arguments for why this is a reasonable conjecture. So let me try to make an argument with Penrose's cosmic censorship hypothesis. So those of you who've taken general relativity courses, they will be very familiar with this space-time diagram of the black hole. So here I'm looking at a black hole with a charge smaller than the mass. So horizontal axis is the radius. The vertical axis is Schwarzschild time. So here we have an observer outside of the horizon of a black hole. Now, inside of a black hole, there's a singularity. But the observer outside is completely shielded from this bad thing that happens in the inside of a black hole. So, because the observer cannot see anything that emerges from this. However, the equations of general relativity allow for solutions with charge greater than the mass. So, and for solutions with charge greater than a mass, you have this bad situation that the observer outside of, well, the observer far away from the black hole center sees this naked singularity. So the observer sees stuff coming from the singularity, and a mathematician cannot really set up a Cauchy problem. So this is bad. And so I'm now going to paraphrase what Penrose argued. And the way I'm going to paraphrase it is, I'll say the effective field theory, which is general relativity, without any quantum corrections, allows for such pathological solutions. But the full theory, the ultraviolet physics, will not allow for such solutions where the external observer is not shielded from the singularity and the non-unitarity. Okay, so this is Penrose's cosmic censorship hypothesis. And I'm now going to translate it to cosmology by replacing the singularity by the modes, by the Trans-Planckian momenta. And I'll replace the black hole horizon by the Hubble horizon. And note that what I'm doing is I'm actually going from position space to momentum space. So I'm having a momentum space version of what Penrose did. Okay, so I think you should find it reasonable to replace the singularity by Trans-Planckian momenta, but I need to argue more why I replace the black hole horizon by the Hubble horizon. And the reason why I take the Hubble horizon, it's a very conservative choice. I say fluctuations only oscillate on sub-Hubble scales, and fluctuations freeze out and become classical on super-Hubble scales. So, well, it may not be okay for fluctuations to become to emerge from the Planck region and become larger than the Planck length, but as long as they remain sub-Hubble, they will not classicalize. So this is the justification for choosing the Hubble horizon in this substitution. It's a conservative choice. Now, there's also a non-unitarity which is associated with effective field theory in an expanding universe. And in effective field theories, you always have to have an ultraviolet cutoff, and it has to have constant physical scale. And if you want to maintain constant physical scale in an expanding universe, then you have to constantly create new modes, because the physical wavelength of a mode is increasing as the universe expands. So there's a non-unitarity which is associated with effective field theories in an expanding universe. And if we want the observer to be shielded from modes which undergo this non-unitarity, then we have to demand that no Trans-Planckian modes ever exit the Hubble horizon. Okay, so this is two sets of justifications for this Trans-Planckian censorship conjecture. And here's the implication for inflation. And I'm getting close to where I will end now. So here I draw the space-time diagram of inflation again. So time is the vertical axis, space is the horizontal axis. Ti to tr, this is a period of inflation. And the way that I drew this diagram is I drew this as marginally satisfying the TCC. So inflation is exactly long enough that the Planck length becomes Hubble length at the end of inflation, but not more. So inflation cannot last any longer than I drew it to last here. Otherwise, the TCC would be violated. Now, if inflation is to be successful, then stuff that we see today has to emerge from inside the Hubble radius at the beginning of inflation. And I drew this criterion as being marginally satisfied as well. So now you see, where does this line lie? Obviously, the closer this line, which is a Hubble radius, lies to the Planck length, which is this line, the more difficult it is for me to realize both conditions. So the Hubble rate depends on the energy density during inflation. So the higher the energy scale of inflation, the closer this Hubble radius is to the Planck length. The lower the energy scale of inflation, the easier it is to satisfy the TCC. So now it's simple math to work out these two criteria, the TCC criteria, upper bound on the duration of inflation, inflation successfully generating CMB anisotropies, lower bound on the duration of inflation. You combine the two, and you find that the energy scale of inflation has to be small. Many orders of magnitude smaller than it usually has to last. And if this is the upper bound on the energy scale of inflation, it predicts an upper bound on the amplitude of gravitational waves. And if you divide the amplitude of gravitational waves divided by the amplitude of the cosmological perturbations, you get this R factor. And the R has to be, this condition means that R has to be smaller than 10 to the minus 30, which means that inflationary models consistent with the TCC predict utterly negligible gravitational waves. Okay, so now, in principle, you could still try to save zero inflation, but not without extreme initial condition fine-tuning. So I'm almost finished. Bouncing cosmologies are completely consistent with the Trans-Planckian censorship conjecture. And you see that from this diagram. Perturbations never come close to the Trans-Planckian region. So more concretely, as long as the energy scale of the bounce is lower than the Planck scale, there's absolutely no constraints on the TCC. Emergent cosmologies, as long as the energy scale in the emergent phase is smaller or equal to the Planck scale, absolutely no constraints with the TCC. So basically, let me now have a preliminary conclusion And then I will open it up for questions, and maybe the questions will allow me to show a few more slides. So I hope to have convinced you in the second half of the talk that inflation does not naturally emerge from superstring theory. And if you accept the Trans-Planckian censorship conjecture, then inflation is highly fine-tuned. And inflation, alternatives to inflation seem to have no problems. So I want to conclude here, but I will allow myself the freedom to show a few more slides if they are the right questions.
Excellent, thank you very much. Sorry, what's that?
I think I kept to what the time that you wanted me to talk.
Absolutely, yes. It's precisely 45 minutes. Good. So let's open the floor for questions. Okay. Maybe I should start with a question. So did I? I'm not sure I fully understand the two non-inflationary scenarios or paradigms, as you said. I think the bounce paradigm and the emergence paradigm. From what I understand is that you haven't. So these are very generic scenarios. These do not yet come with like an underlying physical theory or some sort of specific mechanism which creates the emergence or the bounce, right?
Although I do have these extra slides, you see. There is a underlying motivation. So maybe I will show a couple of.
Okay.
So let me talk about the bounce. Among bouncing cosmologies, the ekpyrotic bounce has big advantages. And the ekpyrotic bounce is a scenario where the universe is very slowly contracting. And in order to get this very slow contraction, unfortunately, if you work with Einstein's equations, you need to introduce a scalar field. And the scalar field has to have a negative exponential potential. But if you do that, then anisotropy are diluted, you get spatial flatness, it's a local attractor, maybe even a global attractor in initial condition space, so good features. Now, how do you get this ekpyrotic scenario? Well, negative exponential potential. Negative exponential potentials are ubiquitous in string theory, okay? So this is the negative exponential potential. This is the solution of the equation of motion for this negative exponential potential. And you can ask, how far do you roll in one Hubble expansion time? And you find you roll much less than m Planck. What is the slope of the potential? Much bigger than 1, the relative slope. Second derivative, much bigger than 1. So completely consistent with the Swampland criteria. And it has a stringy motivation. So this is, I can also elaborate for my favorite alternative, which is actually the emergent scenario. This is string gas cosmology. And as the word says, it comes from string theory directly. So.
Okay. Great, thank you very much. I mean, presumably that's one way to get a bouncing cosmology, but there's also people who claim that you get bouncing cosmologies in using loop quantum gravity as a basic theory, or also other physics. So I think it might be quite general.
Right. Now you see what I described here is how do you get this contracting phase, not how you get the bounce.
Right.
I didn't describe it, how you get the bounce. And indeed, the bounce you can get with loop quantum cosmology. You might be able to get it. But here I proposed something else. This is recent work. It's the S-brane bounce. So here what we did is we just realized that if you start with string theory, you start in a contracting phase, then you reach a point where many new degrees of freedom have to be added to the effective action. This means you get an S-brane. And then immediately you get a continuous bounce. And you get a scaling around spectrum of both cosmological perturbations and gravitational waves.
Mm-hmm. So, I mean, if I understand this correctly, it means that there's a desirable consistency and coherence within the paradigm of string theory that you get here. But of course, it doesn't.
This is what I'm trying to argue. But
yes,
yeah, I mean, the second half of my talk,
yes,
there are going to be people who will disagree with me on this.
Okay, sure, yes, but that's what I understood the argument to be. But of course, none of this would touch if we would, consider these things outside of a string theoretic paradigm.
That's right. So here, this scenario, you can consider outside the string theoretic paradigm. At least this part is completely outside.
Okay.
And then I use the string theoretic paradigm to give you this particular type of bounce.
Mm-hmm. Okay, great. Maybe I should remind people how to ask questions. So I'm not sure everybody has discovered the raising hand symbol. In case you haven't, feel free to say question or finger in the chat. I hope you all see the chat function. So Francesca, this is raising a hand. Yes, there you go. Okay, Francesca.
Thank you, Robert. This was extremely clear as usual of yours. Thank you very much. Of course, my concern is that I see a certain circularity of your argument because it's all based on a trust on string theory. So your argument seems to be, if I trust string theory, then I would prefer an alternative scenario to inflation, for instance, the periodic one. So I'm very curious because you have worked on so many different cosmological models. While you were talking about the bounce, I was thinking, for instance, to the matter bounce. And it seems to me, so I'm curious of where you are now. It seems to me that you, from what you were saying, this ecperiodic version, this version of the ecperiodic model seems to be the one that you are favoring at this particular moment.
Well, see, among bouncing models, I think there's a strong preference for the ecperiodic. And the reason for that is that it solves the homogeneity problem, it solves the anisotropy problem, and it solves the initial condition problem. So, and it also creates, it also solves the flatness problem, which the matter bounce does not. The matter bounce is actually an unstable trajectory. So I think, so I have among bouncing models, I have a preference, and I think these are my arguments for this preference. But now, among the different scenarios, I don't, my preference is still something that's the emergent scenario.
Okay.
So maybe you were trying to provoke me to talk a little bit about the emergent scenario.
Just one more thing about the ecperiodic one, because the usual concern, at least my concern with respect to the ecperiodic one, is that we don't like, one of the reasons not to like inflation is that you have to add this scalar field that comes from nowhere. And with the ecperiodic bounce, you also have to introduce a scalar field, but it seems from your presentation seems to be that you're making it more natural on the ground of string theory, deriving the particular shape of this scalar field.
That was an argument, but it was not a very strong argument. Because you see, if you listen carefully, I said that negative exponential potentials are ubiquitous in string theory.
Yes.
This is correct, but are they steep enough?
Ah.
This is a question mark. They may actually not be steep enough. In which case you would get something that's much closer to the pre-Big Bang scenario. And this is something that we are working on now.
Very good, thank you. If you wanted to go ahead with your suspect of a provocation and talk about the emergence scenario, I would be very happy.
Now, I'll first wait. Maybe there are other questions.
Actually, there are other questions, so maybe we should get to those first and then talk about the emergent scenario, if you don't mind. So, Julius, please.
Okay, yeah, thank you, Robert. It was great as always. I have maybe let me start with this one. So I think I see the analogy between the cosmic censorship conjecture and the Trans-Planckian censorship conjecture. But what I'm wondering is that at least for some versions of the cosmic censorship conjecture, they not only come with a conjecture, but also with something like a conjectured mechanism. So for instance, for some versions of the strong cosmic censorship, that could be the blue shift instability of the Cauchy horizon in the interior. Is there something similar that naturally comes up, comes together jointly with the Trans-Planckian censorship?
Yeah, this is a very good question. And there's the debate about whether de Sitter space is stable or not.
Right.
So in fact, in my opinion, it is very clear that it is unstable. So Polyakov has had arguments about instability of de Sitter for a long time. The way that I like to phrase it is that if you have a short period of accelerated expansion, you will perturbations will become long wavelength, and each long wavelength fluctuation mode will act as a negative contribution to the cosmological constant. So the perturbations generated during inflation will tend to mask the cosmological constant. So I think the answer to your question is yes. And I think it has something to do with the instability of de Sitter space, but this has not been worked out in detail. Because it needs to be quantitatively strong enough. This back reaction effect is probably not strong enough to quantitatively give the Trans-Planckian conjecture.
I see. So in the Polyakov arguments, there would be some, if they work, there would be some sort of numerical estimate for how strong the instability of de Sitter would need to be. Did I get that right?
Okay, I have to pass on this question because I never fully understood the paper. So I don't know what he claims for the instability. If you work in perturbation, in the leading order, to leading order in perturbation theory, you can estimate the time scale. And then you get a time scale which is right along for the instability.
Okay, thank you very much. I may email you about this, if that's okay.
Okay, thanks. Mike, please.
Hi, Robert. This was fun. As I think you know, I'm very interested in the subject, and I was hoping to maybe push you to try to get a view out of you that I think might be in the background here, but I'm not positive. And this in particular has to do with how you set it up so that there's pressure on inflation because you'd have to adopt highly fine-tuned, super unnatural conditions. And then you offered the toy models of the other scenarios as a suggestive measure to say it would be natural on a whole host of other early universe scenarios. And I wonder why you see that as the direction to go, and not that by holding on to inflation and censorship conjecture, we get a really interesting kind of constraint to check for while we're working out our quantum gravity theory.
So you want to hold on to inflation and the TCC?
I'm not sure I'm committed to wanting that, but yeah, that's
no, but you want me to. Okay, so you see I just don't see this as I don't think you'll be able to get a scenario which is natural. See, you don't want to highly fine-tune your inflationary model in order to be consistent with the TCC.
So I guess a way of restating the question then is, why do we not want a highly fine-tuned model? There are plenty of other cases in historical sciences where the opportunity to have a tight constraint that requires us to adopt highly fine-tuned conditions is extremely informative for sort of grander aims. And why is this not one of those cases?
Because inflation was invented to solve fine-tuning problems on the cosmology side. And if you just replace that by fine-tuning on the scalar field model building side, you haven't made any progress. So this is what I would say. But maybe this is too naive a view.
No, that's great to hear that that's
you see, there's another way to hold on to inflation. And you see, I was talking about effective field theories. So if you can get inflation in a way that is completely non-perturbative, then the objections disappear. But because then there would be no reason to impose the TCC. Because if you have a complete non-perturbative theory, then there's no Trans-Planckian region of ignorance. So this idea that you have a Trans-Planckian region of ignorance, that is only important if you want to work at the level of an effective field theory. But this is what all practitioners of inflation do, almost all.
Sure.
There are a couple of interesting exceptions now in the literature. There's a paper by Dvali and Gomez, in fact, a series of papers, where they view de Sitter as an extremely non-perturbative condensate of gravitons built on top of Minkowski space-time. And there's a similar construction by my colleague Keshav Dasgupta with Shudo Brahma, and the second paper is also with Helitz and Bernardo. They have a similar, very non-perturbative construction of de Sitter. In the second approach, it is short-lived, so it is so consistent with the TCC. So basically, I think that if you want to hold on to inflation and avoid and be consistent with the spirit of the TCC, then you really have to go non-perturbative.
I see. Thank you.
And that's definitely a role to do. But you see, most people think that inflation happened. If you read astronomy textbooks, they say the universe started with the period of inflation. Therefore, I wanted to give you the strong argument that we actually do not know this. There are alternatives.
I think that's just a bad habit we're in.
Well, it's a bad habit, but it's misleading the students. It's misleading the public, so it's not very good.
Yeah, okay, thank you. Nick has a question.
There we go.
By the way, Mike, I still owe you an answer to your email.
That's
So
fine.
thinking,
It's been a bad term for me. I've been overworked.
So yeah, thanks. So thanks for the talk. There was like a lot there to sink in, and some of the questions I have are sort of more clarificatory questions. I think still at this stage, I think I do see what the overall argument is. I was going to make a quick comment about the kind of misleading the students and public. If you're right, it's certainly been the case at the Adler Planetarium here in Chicago for at least the last 10 years. When you go down to the story of the universe, that's inflation is definitely on their map there. Right. So the bits I wanted to ask about, and I don't know, sometimes it's usually a mistake to ask sort of two questions, but I guess they do kind of go together. And they were, because they're both about the motivations for the TCC again. I think I get the general idea, but in the case of your first justification, I take it that with Penrose, what's ultimately driving the cosmic censorship hypothesis is a sort of failure of determinism, or worse, if there are naked singularities. And I couldn't quite see what the analog of that was, in particular in the TCC case when we went to some momentum space.
It is failure of determinism. It is failure of determinism at the level of where we can trust the equations. So if we work in the context of an effective field theory, we have no right to talk about wavelengths smaller than the Planck length.
So, okay, so let me follow up on this one then a bit. I mean, the way I understood Penrose, the way I understood sort of cosmic censorship, it's a kind of, what the worry is that, I'm not worried, that the ultimate motivation then is going to be, well, the world just shouldn't be put together in a way that leads to this kind of indeterminism. Whereas what I'm understanding from what you're saying is it's more of a kind of subjective epistemological kind of worry. We don't know, so we shouldn't have a theory that talks. And so that talks about these things. Am I getting this right? So Penrose is just like, this is just the wrong way for the world to be put together. And that doesn't seem to be quite the flavor of the TCC.
No, I'm saying that so I am twisting Penrose's wording, because I'm saying that there's a theory beyond general relativity, and that theory must prohibit these pathological solutions. So it's not just that we are not made this way. We don't have any black holes in our universe with charge greater than a mass, but it is in principle impossible to have such objects if we use the full theory.
But that's...
So you spotted...
That's what the conjecture says, or that's what motivates the conjecture?
This motivates the conjecture, and therefore it is what the conjecture says.
Okay. Okay. I mean, I had the other question for the violations of unit on the other side, when the bad thing that happens in the other argument is something like a violation of unitarity is observed. So is that then ultimately coming to the same sort of picture? If we knew the full story, we sort of know we couldn't see these. We shouldn't see. They shouldn't. If the final theory is unitary, we wouldn't see them, and we think it is. So that's what's motivating them.
That's right. So I'm assuming unitarity. I'm assuming that any good quantum theory has to be unitary.
So whatever the final theory is would actually, or whatever the deeper theory would prevent us from seeing these, so we can impose that as a criterion on our current theories.
This is imposed in this second justification.
Okay, thanks. I think I understand how what motivates them better. The perspective that was helpful. I see another question or two in the chat. I don't know if Chris wants to read them.
Yeah, but it's good. It's good that you bring this up, because this kind of these justifications you won't find in print yet.
Great. Yes, we do have. Okay, so Mike has a finger on this. I'll give that precedence then.
So this is just a quick question with respect to the cosmic censorship comparison. I know Penrose put the conjecture in a few different ways all at once, but at least one of them was with some appeal to entropy, which I would take to be explicitly a nod toward a future full theory. Is that not? You said you were twisting Penrose's words by putting it in the context of a full theory, but is that not already there in Penrose's thinking from the start?
Okay, I'm not a very good historian of physics, so I don't know.
I should say I don't know either. This was a confusion in the dialogue, not my coming with greater awareness.
Okay, there's two questions from N. Femto in the chat. Let me read them. The first one is, what is your opinion on the Poincaré universe model as alternative, please? And the second one is, what is the Cauchy problem and the Cauchy surface exactly based on?
Okay, so I can only answer the second question. So when I spoke about Cauchy surface, we always work with equations, and equations need initial conditions. So we need to have a time where we impose initial conditions. And we need to impose initial conditions everywhere in space. So this is the Cauchy surface. It is a surface of space at the initial time where we set up the initial conditions. And so this is Cauchy surface. And when mathematicians talk about Cauchy problem, they mean solving differential equations with fixed initial conditions. So when I said Cauchy problem, I don't mean something problematic. I mean a Cauchy problem, a mathematical problem which a mathematician will solve.
Okay, great, thank you. So I think it's time to look at the emergent scenario then. Would you mind telling us a little bit more about it, please?
Right, so I'll give you one toy model for the, so actually before doing that, let me mention one thing. So inflation, there's another very nice aspect of inflation, and that's a historical aspect. Inflation was worked out before most of the data was available. And the fact that inflation is consistent with the things that we've now subsequently measured, it's a big success. So from a historical point of view, there's something that speaks in favor of inflation, because inflation made predictions. So therefore, in order to really work on alternatives, we have to develop alternatives to the level that they make predictions with which they can be distinguished from inflation. And so here I have the prediction from this bounce in cosmology, from the ekpyrotic bounce. So early universe scenarios don't give exactly skein invariant spectra, but slight tilts of the spectra. N sub s is a tilt of the cosmological perturbations, N sub t is a tilt of the gravitational waves. N sub s is usually 1 minus N sub s is actually the tilt. So for these stringy mechanisms, we predict a positive tilt for the gravitational waves. Inflation predicts a negative tilt. So just to the level that we actually work out predictions with which these different scenarios can be distinguished with future observations. Okay, so now the model, this toy model of the emergent universe is to have some space and have it filled with a gas of fundamental strings. Now, fundamental strings have degrees of freedom which are different from degrees of freedom of point particles because strings can bind space. So also strings have oscillatory modes, like you can pluck a violin string and you can create many different sounds. So a given string has many different modes. So this leads to the fact that if you take a gas of strings in a box of radius r, the temperature will never diverge. The temperature, if you shrink the size of a box, you shrink r, and I plot it logarithmically, the temperature will first rise, it will level off, and then eventually decrease. There's a symmetry between large and small. Also, this looks like a place where you might start the dynamics, like a long-lived but ultimately metastable state. So this is the idea that you start out the universe with a gas of strings at this temperature. You live there for a long time with constant size. This is a model for this emergent phase. And then eventually what will happen is that the winding modes, the modes that prevent space from expanding, will be able to meet each other and decay, but this can only happen in 3 dimensions of space. So you'll have a phase transition in which 3 dimensions of space and not more will be liberated to become large. This is this phase transition. Okay, so this is this toy model for the emergent universe. And then you can show that thermal fluctuations of strings in this phase give rise to a scale invariant spectrum of cosmological perturbations. And you see, this is the basic ingredients are stringy. So this is just to give you a glimpse.
Excellent, thank you very much. So Francesca, did you have a follow-up on that?
Not really, just to, maybe I just wanted to highlight that there has been some recent version of loop quantum cosmology that look more similar to this emergent scenario. So maybe it's...
Are you referring to some of Bourgeois' work, or is that?
No, I'm referring, so there's been some developments trying to derive the cosmological sector in loop quantum gravity using a technique that is called quantum reduction, instead of imposing the symmetry reduction at the classical level before the quantization. And there are some new terms such that instead of having really a full bounce, you have more like a semi-stationary phase from which then the expanding phase emerges. So it's maybe interesting to know that on both sides, also in loop quantum gravity, there is maybe something similar that is considered presently.
Can you get a handle on the fluctuations in this case?
Yes, it has been studied. There is a paper, but actually I don't remember exactly the detail. I think in particular it could be interesting to see things like the tilt, the spectrum, and so on. But I'm sorry, I don't remember the details.
But see, I'm wondering whether you could get holographic scaling.
Holographic? Sorry, what?
Yeah, you see in some quantum gravity models, there is a difference in the effective dimensionality of space.
Oh.
And you see, well, by holographic, I mean specific heat capacity going as area and not as volume.
Yeah.
Because if you can get that in your emergent phase, then you would have the right perturbation spectrum.
I can check this. I mean, there is a different issue in loop quantum gravity that has to do with a possible effective dimension in in the deep quantum regime, but I think this has been somehow discarded. This scenario has been discarded. I'm curious about what you said, because a change in the effective dimensionality is related to a break in a Lorentz invariance, and is usually thought as a problem for perturbations. For instance, in some cosmology based on Horava gravity, I thought that this was somehow forbidden. Maybe this is, you're referring to something different.
Yeah, I'm referring to something very different. I'm referring to things that happen in causal dynamical triangulations.
I was thinking of that kind of change of dimension. That is present in causal dynamical triangulation, is present in Horava gravity and so on. So the holographic scaling is something else.
Right. Anyway, you would, that would be the thing to study. What if you have a long-lived quasi-static phase, then it would be interesting to study the things like specific heat capacity.
Okay. So this is present in the string gas scenario, and
yeah, you see, the way that this appears in string gas cosmology is that long strings are equivalent to point particles in one less spatial dimension.
Sure.
This is the origin of the holography. But holography should be much deeper. And you might be interested in looking at the recent paper by Waffa and collaborators just a couple of months ago, where they have a topological phase. So they describe this quasi-static phase as a topological phase of gravity.
Okay. Thank you. I'm very interested to dig more in this literature. Thank you very much, Robert.
Yeah, we should keep in touch.
Okay, great. I do have another question, if you allow. It's sort of a central point, an important point in the argument, where just to make sure that I get this right, the main trouble that inflation got into was because we were trying to fold it into the sort of a string theoretic paradigm, to have it sort of give it a fundamental theory, give it sort of a physical mechanism to produce the fields needed for the inflation. Is that right?
Well, not quite, because you see, if you go back to inflation, you need these conditions, condition 1 and condition 2. And these conditions don't look natural if you just write down potentials where you don't tune any parameters, then you will violate that. So,
okay, so that was
effective at the level of effective field theories. You can do anything you want, so there are no rules. So nothing prohibits you to get these conditions. So it's more like, for me, string theory is a way to, maybe not the only way, but a way to give rules for what constrains effective fields.
I see. So really it would be more correct to say that, as you said in response to Mike, that the problem is really that inflation is trying to solve a fine-tuning problem, and itself requires some fine-tuning here.
Yeah, that's right.
Okay, thank you very much. Nick, I think, had a hand up, but it's down again. Nick, did you have a question?
Sorry, finding my unmute button. Well, I don't know. What time do we actually want to finish? That's the.
Well, sort of now-ish.
Yeah, let me think about it some more. I think maybe I figured an answer, so I want to get us started again.
Okay. Well, in that case, please join me in thanking Robert once again for a very nice, a very clear talk. Thank you very much. Okay, so if you let me, I'll make a brief announcement. We will have another Beyond Spacetime talk in 2 weeks from now in the same slot, time slot, with Mike Schneider, who was here and probably he is still here somewhere. We'll be giving a talk in 2 weeks. So please stay tuned for that and be well until then. Thank you very much, Robert, once again.
Yeah. And
Bye.
will you also send
Bye,
me
everyone.
the announcement for that seminar?
Sorry?
Will you also send me the announcement for that seminar?
Yes, I will. Good.
It is,
I can do that. No problem.
it's in theme with today's presentation.
Yes. Yeah. Good. So thank you very much.
Yeah, thank you very much. That was really, really great. I enjoyed that.
Thanks all of you for listening.
And so be well. I hope you'll have a nicer weather in south of the Alps than we do up here. You're not so much in the fog.
Right.
Okay.